We're now ready to talk about another application of double and triple integrals. We've talked about finding area, finding volume, finding average value using double and triple integrals. Now what we want to compute is what's called the center of mass, or the location that's the average location of all the atoms that make up a particular object. So in a sense, the center of mass is if we took all of the atoms in the object and piled them up in one location. It would then behave the same as the regular object. Now we're going to be looking at two types of objects. We're going to be looking at what is essentially a two-dimensional shape called a lamina. It doesn't have to be rectangular. It can be a triangle, a circle. It can be a totally irregular shape, but it's essentially two-dimensional, has length and width, but no depth to it. And we call that a lamina. Then we're going to be taking a look at three-dimensional solids. So this is an example of an ellipsoid. So if it were solid all the way through, and let's suppose that one end of it is made of lead and the other end of it is made of styrofoam, we want to know where is the location that is the average location of all the atoms and molecules that make it up. Now, you know that lead is more dense than styrofoam. So you would expect that there are more atoms and molecules on the lead side than there are on the styrofoam side. And that's going to shift the center of mass. Now, that's different from what we call the centroid. The centroid is simply the geometric center of the shape, pays no attention whatsoever to the density of the object or the number of atoms and molecules per unit volume. In that case, we would expect for an ellipsoid that the centroid would be located in the dead center of the ellipsoid, so in the center in all three directions. And that would be the geometric center of it. We're also going to take a look at the center of gravity, when the center of gravity and the center of mass are the same, and when in fact they're different objects. We'll also look at when the centroid and the center of mass are the same, and when the center of mass, the centroid, and the center of gravity are all in the same location. Let me share my screen with you, and we'll get started. Let's go ahead and talk a little more in detail about the center of mass, center of gravity, and the centroid. The center of mass, as we said, is like an average location of all the atoms and molecules that make up a substance. If one end of it is made of lead and the other end of styrofoam, the lead side has more atoms and molecules than the styrofoam side, so the center of mass shifts to that side. If we think about the center of mass is the location where if you were able to pin it to a wall, you would be able to spin it around that point without any wobble. So it spins around the center of mass without any kind of jarring or juddering motion. If you have a washing machine, then it's rotating around the center of mass. And you know this happens whenever the washing machine gets what we call out of balance. What we really mean is that the center of mass has shifted and it's no longer in the center of the rotating tub. If all the towels in a wash load end up on the same side, that shifts the center of mass toward the side where all the towels are. And then it will start to vibrate and shake because it's no longer spinning around the center of mass. If it spins around the center of mass, there won't be any wobble. If you have a piece of machinery that has a part that rotates, then you need to have it attached to the center of mass. Otherwise, it will set up a vibration that will grow stronger over time until it eventually rips the machinery apart, literally, as in it could explode. The washing machine, fortunately, has a shutoff when it senses that the load is out of balance or that the center of mass has shifted. Otherwise, your washing machine could, in fact, explode. Now, the center of mass, oddly enough, doesn't actually have to be on the object. We think about this donut on the right, we can assume that the donut is more or less uniformly dense. In other words, the number of atoms and molecules per tiny little cube of volume is the same throughout the donut. In that case, the center of mass is actually in the dead center of the hole in the donut. So it's right there in the center. If you think about a horseshoe is generally made of the same kind of material throughout. And so we're going to have the same number of atoms and molecules per tiny cube of volume throughout the horseshoe. But because the horseshoe is connected on one end and open on the other, it shifts the center of mass down towards where there are more atoms and molecules. Now, it is a symmetric shape, so it will still be on the line of symmetry that goes through the whole thing, but it's going to be shifted somewhat down towards the bottom. So if we have our line of symmetry here, then our centroid is going to be somewhere in that location. And that's where our center of mass is going to be. That's not the centroid. The centroid is actually the center of the object, which was probably a little bit above that. In the donut case, the centroid and the center of mass are the same because the donut is uniformly dense and it's a symmetric object in all respects. So the centroid is the dead center of the hole, which of course is also where the center of mass is. So it would be right there. Note that in both the horseshoe and the donut, the center of mass is not actually on the object itself, which means that you cannot pin a horseshoe to any kind of wall and have it spin freely without a wobble. It will wobble because you're going to have to attach it at some place where it has material. Likewise, if you attach a donut where it has material, no matter what you do, it's going to ka-chunk as it spins around because you cannot attach it at the center of mass. And again, we think of the center of mass as sort of the weighted average location of all the atoms and molecules that are present in the object. Now let's compare the center of mass to the center of gravity. Now the center of gravity is not a measure of the average location of all the atoms and molecules, like center of mass is. Instead, center of gravity is sort of a weighted average of the effect of the gravitational field on the atoms and molecules. So if you're on Earth, the Earth itself, being massively large, exerts a gravitational field and it pulls on all the objects around it. Now, if you're relatively small, as in a human being, even an RV or a dump truck or a semi-trailer, compared to the size of the Earth, then the gravitational pull is roughly the same at all points on the object. But if you are, say, the Empire State Building in New York City, well, it's very massive and long. And because it is long, it turns out that the center of mass and the center of gravity are not in the same location. When you have a uniform gravitational field, then the effective gravity is the same everywhere. But because the Empire State Building is so tall, then the gravitational field actually changes from the bottom of the high-rise building to the top of the high-rise building. And it shifts the center of gravity down 1 full meter from where the center of mass is. So it shifts the center of gravity towards the source of the gravitational field, which of course is the center or core of the Earth. So if we're looking at this image down here, in the image on the left, we're in a uniform gravitational field, which means that the effective gravity, say, on my head is the same as it is on my hip or the same as it is on my foot. In that case, my center of mass and my center of gravity are the same location if I'm in a uniform gravitational field. But the Empire State Building, being so tall, is not in a uniform gravitational field. The effective gravity is stronger on the ground floor than it is at the top of the Empire State Building. And because of that, the center of gravity is shifted down towards the source of the gravitational field, the center of the Earth. But the center of mass is unchanged. Now, if you think about the center of mass is going to be the same whether you're on Earth or on the moon or in the vacuum of space. It's the average location of all the atoms and molecules. The number of atoms and molecules doesn't change no matter where you are, but the effect of gravity does. So the center of gravity will be very different on Earth than it is on the moon and in the vacuum of space. Again, center of mass and center of gravity are the same if you're in a uniform gravitational field. On Earth, this means that you have to be relatively small compared to the size of the Earth. Now, it is technically true that there is more gravity on my feet than there is on my head, but the difference is so tiny, we say it's negligible. And we say that essentially my center of mass and center of gravity are in the same location. Now, how do we think of the center of gravity? If the center of mass is the place where you can pin it to a wall and spin it without any kind of wobble, then what is the center of gravity? Well, the center of gravity is the point where you can balance it on the tip of a pin and it won't rotate and fall off, all right? So the center of gravity is when the pull of the gravitational field, and I can't quite get it, is the same in all directions. So it stays put, balanced on the tip of the pin, which you'll have to imagine because I can't get it to stick. So that's a difference between the center of gravity and the center of mass. The center of mass, if we affixed it, it would rotate without a wobble. The center of gravity, it balances without wobbling and falling off. Now, let's take a look at the centroid. The centroid is the geometric center of the object. So the geometric center is just the center with respect to geometry. It does not take into account the density of the object, nor does it take into account the gravitational field. It ignores gravity and it ignores density. It just looks for the middle of it, if you will. Now, if the density of the object is uniform, and that would happen if it's made up of the same material all the way through, then the centroid and center of mass are in the same location. So this particular object is made up of the same kind of material throughout it, which means that the center of mass and the centroid are going to be in the same location, which is going to be in the dead center of the ellipsoid. And because it is so small, the center of gravity, I can consider it to be in a uniform gravitational field. So the center of gravity is also in that same location where the centroid and center of mass are. Now let's go ahead and look at some images of what a centroid is. If you have a triangle, you can find a centroid by cutting each side in half and drawing a line from the midpoint of each side to the opposite corner or vertex. If you do that, then these three lines will cross at the centroid, which is the geometric center of the triangle. It won't matter if this end is made of lead and this end is made of styrofoam. The centroid's just the geometric center. There is actually a town in Texas that it is in the geometric center as computed by computers of Texas. And then notice here as well that we can have a geometric center that is not in fact on the shape, just as we had a center of mass that was not on the shape. So let's go ahead and summarize what we've learned about center of mass, center of gravity, and the centroid. If the gravitational field is uniform or constant, then the center of mass and center of gravity are roughly the same. And it applies if you're like semi-truck size or smaller. It doesn't apply to the Empire State Building because it is so tall, it's not in a uniform gravitational field. If the object is uniformly dense, meaning the density is a constant, same number of atoms per unit volume, then the center of mass is equal to the centroid. So if I'm in a uniform gravitational field with uniform density, then all three of these are going to be equal to each other. Now we want to talk about something called a moment. We're going to look at moments and moments of inertia in this section. We'll talk about moments of inertia at the end of this section. We're going to talk about moments first. Moments of inertia are a resistance to being moved or rotated. So if you have something positioned, it's the resistance, it's the force required to get it to move, all right? The moment we want to talk about right now, since we're going to be looking for the center of mass or center of gravity, is the tendency to rotate off of an axis. So we tend to split the moment into two components, the horizontal and the vertical. So we have uppercase letter M sub X and uppercase letter M sub Y. So uppercase letter M sub X, the moment with respect to X, is the tendency to rotate off the horizontal axis. So if you have some object right here and it rotates off X, what's actually changing is the Y value, oddly enough. So when you rotate off X, what's changing is Y. Now, if you talk about the moment with respect to Y, then you're talking about the tendency to rotate off the vertical axis. But if you rotate off the vertical axis, what's actually changing is this distance here, which is actually X. So when we look at what we call the discrete or multiple objects case, we're talking about having a number of point masses or weights, if you will, in different locations in a two-dimensional system. So the question is, what will make it balance on this center of mass? Well, in order to figure out where it balances, I need to find the moment for each individual object. So the moment for each individual object, since it's small enough to be considered a point mass, is going to be given by the mass of the object times the distance from that particular axis. So if I want the moment in the X direction, then it's going to be the mass of each object times its Y value. Because again, if you're talking about the moment with respect to X, you're talking about the tendency to rotate off the X-axis, which changes the Y value. So you need to multiply the mass by how far it is away from the X-axis. You're going to need to balance that out. This is just like seesaws, right? This is a teeter-totter. We need to balance it out. So the total moment with respect to X is the mass of each individual point object multiplied by its Y value, and then we add them all together. The moment about the Y axis is going to be this tendency to rotate off vertical, which is going to change the X coordinate. So again, we take the mass of each object multiplied by its distance from the Y axis, which is its X value, and then we add it up for all of the objects in my system. And then I have to figure out where is the center of mass. So it turns out that our formula for center of mass is going to be pretty much the same throughout this entire section. It's the moment with respect to Y, which again, this is rotating off Y, so it actually changes the X value, divided by the mass for the X coordinate. The moment with respect to X, which actually changes the Y value, divided by the mass will give me the Y coordinate of the center of mass of this system. Now, this is if we can pretend that each of these little boxes that you see here is uniformly dense, and I can consider all of the mass of the object to be in one location. We call that a point mass. So now let's take a look at what we call the thin plate or lamina case. So you may have heard of laminated countertops. It's a flat sheet, basically two-dimensional when you laminate something. So let's suppose that we have a lamina with uniform density. In other words, it could be like my cardboard piece right here. It's cardboard throughout, so at every point the density is the same. then we can again find where the center of mass or the centroid is. Note they're the same because we have uniform density. By taking the moment with respect to y and dividing by the mass for the x coordinate, the moment with respect to x divided by the mass for the y coordinate. Now, what happens if the lamina does not have uniform density? What if one end is made of lead, then we have, I don't know, aluminum in the middle and tungsten on this end? Well, then the density changes as I move across the object, which means the mass also changes as I move across the object, which is going to shift the center of mass from the geometric center, which of course would be on the line going through the two diagonals in the center. If that's the case, where the density is not uniform, like you have a mixture of materials, then we'll have to find the mass by integrating across the region. Now let's review what we learned from Calculus 2. In Calculus 2, we had a series of formulas for computing the center of mass. However, we were only able to work with it if the density was a function of one variable, but not two. Now, you know that's not realistic because density doesn't tend to only vary in one direction. It'll probably vary in two directions if we're looking at a lamina. So we need calculus 3 in order to figure out what to do when the density varies with respect to both x and y. Sounds like a double integral, right? So, but in calculus 2, we didn't have double integrals. So we forced the density function to be a function of one variable only, either x or y. And here I've written with respect to x over some two-dimensional region, some lamina, some flat region, bounded above by a function f of x, below by the x-axis, on the left side by the vertical line x equal a, and on the right side by the vertical line x equal b. Then these formulas right here gave us the total mass, right? By integrating with respect to x, the density function multiplied by the upper function, f of x, with respect to x. And then we could find the total moment in the x direction, this change in the y value, this tendency to rotate off horizontal, which we take the function, square it, divide by 2, and multiply by the density function. That becomes the integrand. And then we integrate from a to b. And then the moment in the y direction is the tendency to change the x coordinate, x value. And it was given by x multiplied by the density function multiplied by the function that is bounding my region. And when I took the moments and divided by the total mass, then I got x bar, y bar, which is the location of the center of mass. Now, let's go ahead and take a look at the picture so you can see what we're talking about. What I'm talking about is if I had this blue region cut out and it was a flat sheet, and I want to know where the center of mass is. And let's suppose that the density changes as I move across from left to right, because the density is a function of x. Those formulas will let me compute where in this blue region my center of mass is, or maybe it's not on the blue region, though I suspect in this case it probably is. So this is what I'm talking about. Here's the upper function, the x-axis, the vertical lines, x equal a and x equal b. These were the formulas that we used in calculus 2. Now, notice up here that if our density function was actually a constant, if it didn't depend on x or y, it was just a number like 2, then I could factor it out of the integral. And if I could factor it out of the first integral, I can factor it out of the second too. And that means that when I take the moments and divide by the mass, actually, because it's a constant, that density would cancel. Now, it won't cancel in the case where it is a function of x because it becomes part of the integrand and can't come out of the integral. So it can't cancel. However, if it's a constant, it cancels out, which means that if we have something uniformly dense, then the center of mass is not actually dependent on the density at all. And that sounds a lot like the centroid. So we can use the same method to find the centroid. By assuming that the density is a constant, factoring it out and canceling it, we can locate the centroid. Let's take a look at case 2. In case 2, we have a region that looks like this. So we have a curve for the top and a curve for the bottom, but we still have vertical lines for the left and the right. So we're talking about this region here. So how did we adjust our formulas in Calculus 2 to take care of this? Well, basically, we computed it 3 times, right? So we did each one of them twice. So we computed it with f of x, and then we computed it with g of x, and then we subtracted the lower value from the upper value. That's basically what you have. In this case, the total mass is the density function multiplied by the difference in the 2 functions values. Or you could just find the mass under f of x and the mass under g of x, and then subtract the mass under g from the mass under f. That will give you the mass in between the 2. And the same thing is true here. If you want to find the moment in the x direction, the tendency to rotate off of the horizontal, you could just take the upper function squared times the density function, divide by 2, and integrate. And then do the same for the lower function and then subtract the 2. Or you can do them together, but notice that f of x is squared before you subtract the square of g of x. And then, of course, you have the formula for the moment with respect to y. So these were the equations that we used in Calculus 2, but we were very restricted by the fact that the density could only change with respect to one variable at a time because we had a single integral with one differential. What if instead we want the density to be a function of both x and y? Then I need 2 differentials, one for dx and one for dy. And that's got to be a double integral. So let's take a look now at the formulas. And by the way, these can be adjusted to go with respect to y, as I have drawn here. So you can go with respect to y, but again, you can only do one at a time, right? So in this case, rho would be a function of y only, but not of x. So you can only have the density a function of one variable at a time for Calculus 2. Calculus 3, however, we're a lot more free to have a density function that varies with respect to both x and y. So how do we derive that formula? Well, we're going to start with a flat region. This is a 2-dimensional region. This is our lamina, all right, which is just some flat 2-dimensional blob. And we're going to divide it into a grid. So we're going to cut it parallel to the y-axis, cut it parallel to the x-axis. And this is going to create a whole bunch of small rectangles. Now, you know this is the calculus thing to do, right? We chop it into tiny pieces. We make them really small so that we can assume something is constant over that tiny little piece. And the thing we want to assume is constant over the tiny little piece, of course, is going to be the density. So if I make this little square small enough, then the density is roughly constant throughout that tiny little rectangle. Now, it might not be the same as the density over in this tiny rectangle, but over this tiny region, I could consider the density to be a constant. And if that's the case, then I can think of it like a point mass. And if I want to find the moment in each direction, then I just multiply this tiny little rectangle by its distance from each axis. So in this case, the mass times y, and then in this case, the mass times x, right? So when we're looking at that and we come down here to get the moment in the x direction, we're multiplying the point mass, which is basically going to be the density function times the change in area, right? Because we're assuming on that tiny little rectangle that it's constant density. So we take that constant and multiply by the change in the area, our little dx dy, and that will give me, well, mass on that area. And then I take that mass, where this becomes my point mass, times the distance that it is from, in this case, the x-axis, because I have the moment in the x direction, so that's the tendency to rotate off. So how far away from the x-axis is it? What do I need to balance, in other words? And then, of course, we add up the moment for every tiny little rectangle in that two-dimensional lamina. And then after I add them all up, taking the Riemann sum, then I take the limit as the number of subdivisions goes to infinity, or the width and length of each little tiny rectangle goes to 0. And when that happens, I get a double integral over that entire lamina of y times the density function, which is a function of both x and y, with the differential for area dA. And then for the moment in the y direction, it's going to be the same, because I'm assuming on that tiny rectangle, the density is constant. So I can consider it maybe at the centroid, that's where I'm going to compute the moment for that particular rectangle. I'm going to take the distance from the centroid over to the y-axis, which would be x, and then I multiply by the mass of that small little rectangle, which is the density, which is roughly constant on that little rectangle, times the change in area. And that gives me this formula here. So they're very similar. So this is different from Cal 2. In Cal 2, the formulas for the moment with respect to x and y were different, right? One of them was squared, and the other one got multiplied by a variable. They were not the same, and they were both integrated with respect to x, which is a little surprising. In this case, in Calculus 3, the formulas for the moment with respect to x has a y in it, then multiplied by the density function, and the moment with respect to y has an x in it, multiplied by the density function. But their forms are very similar. Now, I do want to warn you that there's an error in the textbook. In the center part, they mistakenly have y sub ij star instead of x sub ij star in the middle. So just watch out for that. And then once we have this, then our center of mass is again given by x bar, y bar, this average location of all the atoms and molecules, where we divide the moment in the y direction by the total mass, the moment in the x direction divided by the total mass. And again, to find the total mass, we just have to add up all the masses of those tiny little rectangles where we're assuming that the density is constant. And that gives us this double integral that you see here. So let's go ahead and work an example. In example 1, we want to think about a triangular lamina. So it's two-dimensional, has length and width, but no depth to it. So it's just two-dimensional. It has corners at the origin 3, 0, and 0, 3. But the density of it varies, both with respect to x and with respect to y. So the density function is 8xy kilograms per meter squared. So as x increases, the density increases. And as y increases, the density increases. So I would expect it to be getting more dense as I move out this way, which would tend to make the center of mass shift out, all right? So I'm gonna again think about subdividing this into these tiny little regions here. And when I look at this tiny little region here, I can assume that the density on that is roughly constant. So the change in mass is just going to be the density times the change in area, since it's roughly constant on that little rectangle. So you can use either the Calculus 2 formulas or you can use the Calculus 3 formulas, but let's go ahead and find the total mass. We're going to do this problem in steps. So example 1 is just first step, find the mass. So go ahead and pause the video to compute it, and then turn the video back on and we'll compare our answers. So in order to compute the double integral, we need to get the bounds on our integration. We can tell that with respect to y, it goes from the x-axis where y equals 0 up to this slanted line, x plus y equals 3. If you solve it for y, you get y equals 3 minus x. So y is going from 0 to 3 minus x. At the same time, x varies from 0 over to 3. So it becomes the limits of integration on the outer integral. And then to find the total mass, I need to multiply the density function, 8xy, by the area differential, which becomes dy dx. So go ahead now and follow through. If you had trouble setting it up, go ahead and pause and work it out. If you did it, let's check your answer. So when I integrate with respect to y, I get 8xy squared divided by 2, or 4xy squared. I evaluate between the limits of y, and that's going to give me 3 minus x quantity squared minus 0, which becomes x squared minus 6x plus 9, and then I distributed the 4x, which gave me a new integrand for the outer integral of 4x cubed minus 24x squared plus 36x. So when I integrate 4x cubed, I get 4x to the 4th over 4, or x to the 4th. When you integrate negative 24x squared, you get negative 24x cubed over 3, or negative 8x cubed. And when you integrate 36x, you get 36x squared over 2, or 18x squared. And you evaluate from 0 to 3, work out a little bit of arithmetic, and when you're done, you have 27 kilograms, right? This is the mass of that object. Now we're eventually going to be looking for the center of mass, which we think is being shifted out because we know that it becomes more dense as x increases and as y increases. So we think it should be out away from the geometric center. So let's go ahead and look at example 2, where we're going to take the next step in the process, where we need to find the moments with respect to x and the moment with respect to y. Now, the moment with respect to x is going to be affecting the y values because you're shifting off horizontal. And the moment with respect to y is going to change x values because you're shifting off the vertical. So we have our two formulas. We can use the same limits of integration that we did last time. We just need to go ahead and compute these. So go ahead and pause the video to work these out, and then turn the video back on and we'll compare our results. In order to calculate the moments, we need to use the formula y times the density for the moment with respect to x, and x times the density for the moment with respect to y inside of the double integral. Our limits of integration are the same as when we computed the mass. So when I integrate the y 8xy, this gives me 8xy squared. So y squared integrates to y cubed over 3. So I get 8/3 xy cubed, which gives me 3 minus x, the quantity cubed, times 8/3 x. Now, I could multiply it out 3 times, but that seems like an awful lot of work. So instead, what I did was a u substitution, where I let u be 3 minus x, which then if I solve it for x means that x is 3 minus u. So I can replace the x with 3 minus u and the 3 minus x with u. The differential dx gets replaced with negative du. And when x is 0, u becomes 3, using my definition for u up here. When x is 3, u is 0, which means that my limits of integration are reversed to what I'm used to. But I have a negative inside the differential, so I can switch the limits of integration and go from 0 to 3 with 8/3 times the quantity 3u cubed minus u to the 4th. So I integrate u cubed and get 3/4 u to the 4th minus u to the 5th over 5, all multiplied by 8/3. When you evaluate between 0 and 3 and simplify, you get 162 fifths kilogram meters. So a moment is the mass times the distance it is from that particular axis that you're rotating about. Now, we also need to compute the moment about the y-axis. So for that one, we use x times the density function. So we get 8x squared y. And we integrate with respect to y first. So we get y squared over 2, which reduces to 4x squared y squared. This time I went ahead and multiplied it out. It's relatively straightforward, which gives us x squared minus 6x plus 9. And I distribute the 4x squared to get 4x to the fourth minus 24x cubed plus 36x squared as the new integrand. And then I integrate with respect to x and get 4/5 x to the fifth minus 6x to the fourth plus 12x cubed from 0 to 3, which also gives me 162/5 kilogram meters. Now, it's not normal that they're the same. In this case, they're the same because it's x to the first and y to the first. So in effect, the change is the same with respect to both variables. So I got the same moment with respect to both variables. Then what I want to do is find the center of mass of this triangle that we have. And I'm going to take the moments that I found and divide by the total mass. Now, we found the total mass in example 1 to be 27 kilograms. So the next thing we do is take our two moments, 162/5, and divide by 27, which ends up giving us 6/5, 6/5. So 1.2, 1.2. So this is where the location of the center of mass of that triangle is. Now, in just a moment, we'll actually picture it on the triangle, but first we want to figure out where's the geometric center, or where's the centroid. Now, this is not necessarily the center of mass unless it's uniformly dense, or the density is a constant. But in this case, density is not a constant, it's 8xy, so it depends on both x and y. But how could we find the geometric center? Well, when the density is a constant, then it can be pulled out of the integral and it cancels, and that gives me the location of the centroid. So the way to find the centroid is to pretend, if you will, that the density is constant. If you want, you can pretend it's a +1, because then it's not going to affect the integrand at all. So when you do this, what you're going to end up with are the following formulas. So we have both a calculus 2 set and a calculus 3 set. So again, if we're thinking of the density as being constant in order to find the center geometrically, then the density gets pulled out of the moments with respect to x and y, and out of the mass calculation as well. And then you have density divided by density in each of the two coordinates, so they cancel. Now, this gives you the resulting formulas that you see here, but these are no longer the moment divided by total mass because we took the density out of it. All right, so the meaning of the numerator is kind of lost. The denominator, of course, is just the area under the curve. So in calculus 3, we are going to take our formula for the moment with respect to x, which is rho times y inside the double integral. But if we're considering rho to be a constant, it can come out. And then my density is given by rho times the differential dA inside the double integral. But if rho is a constant, it could come out. And rho divided by rho, of course, is just the number 1. And so I get this formula right here. So again, we see that the denominator is actually just the area formula, whereas the numerator has sort of lost some of its physical meaning. So we end up with the formulas that you see on the far right. Now, which one is easier to apply depends in large part on the shape of the object that you have and the functions that are giving the two different that are giving the boundaries for your region. So whether the Cal 2 or the Cal 3 is better just depends on the problem. You'll have to try it and see. So what we want to do now is we want to take the same problem that we've been working with, the triangle at 0, 0, 3, 0, and 0, 3, And we want to compute where the geometric center is. Now, again, we could also have taken the midpoint of each side of the triangle and connected it to the opposite vertex and located it physically that way. But I want the coordinates of the centroid. So let's go ahead and apply one of the sets of formulas. You can choose to do either the calculus 2 formulas, or you can choose the calculus 3 formulas. I'll work both this time, but probably I won't do that again. And then go ahead and pause the video while you work it out, and then turn it back on, and we'll compare our results to each other. So I've rewritten the calculus 2 formulas you see right here, and notice that because we're looking for the centroid, we consider the density to be a constant because it won't affect the geometric center. And so the density just drops out, whatever it is. And so we get the integral of x times the function with respect to x from a to b divided by the area under the curve. Now, you can find the area under the curve by integrating if you want to, which I went ahead and did down here. You can see that the area is the integral of 3 minus x dx from 0 to 3. But it is a triangle, right? So you can also do 1/2 the base times the height. So the base is 3, the height is 3, 3 times 3 is 9, and half of that is 9/2. So you get 9/2 square units for the area, which forms the denominator of both x bar and y bar for the centroid. When I evaluate the numerator, I have x times the function. So I have x times 3 minus x. And I go ahead and distribute the x to get 3x minus x squared. I kept the row out there just so that we remember that it's considered to be a constant when you're looking for the centroid. Then I integrated to get 3x squared minus x cubed over 3, evaluated from 0 to 3. Finally gave me 9/2 times whatever the density is. And again, you can consider it to be a positive 1, then it just drops out from the beginning. And then I need to go ahead and take what amounts to the moment here in the y direction, and divide by the total mass, which is 9/2 rho, and the rows cancel and I get 1. So the location of the centroid is 1 unit in the horizontal direction. And then to find the formula for y bar, the location of the centroid with respect to the y, then I need to take the formula 1/2 the function squared and divide that by the area. So I went ahead and computed that down here. This time squaring 3 minus x is pretty straightforward. X squared minus 6x plus 9. I didn't feel like distributing the 1/2, so I pulled the 1/2 out with rho. And then I integrated x squared minus 6x plus 9 to get x cubed over 3 minus 3x squared plus 9x, evaluated from 0 to 3. And when I distributed the 1/2 and simplified, I again got 9/2 of rho. And then the mass, the total mass is 9/2 rho. So when I divide the moment in the x direction by the total mass, I get 1 again, which tells me that the value that I have here is 1, 1. That's the centroid, if you will. So coming up here, the centroid, well, actually, it's right there, dead center of that rectangle, right here at 1, 1. That's where the geometric center of this object is. Now, we found the center of mass previously to be at 1.2, 1.2. So the center of mass has actually been shifted more in this direction. Again, because the density is 8xy, as x increases, the density increases. As y increases, the density increases. So I would expect that moving out this direction towards increasing x and increasing y is going to be where the most dense part is. And that's exactly what happened. It moved out along the identity function. Now, you could also have used the calculus 3 formulas to do it. This time I went ahead and wrote them in fraction form, and I canceled out the density function from the beginning. Now, the denominator is a double integral over the region with an integrand of 1, which is just giving us the area of that region, which we've already computed. It's 9/2. And then the numerator, we have x times dA. This is because we're looking for the moment in the y direction. So we have x times the density, but our density canceled. So when I integrate this with respect to y, I don't have a y, so it's just a constant. And I get xy evaluated from 0 to 3 minus x. And then I distribute the x over the 3 minus x. And I went ahead and took the reciprocal of the denominator and made it 2/9. And then I have 3x minus x squared, which I integrated to get 3x squared divided by 2 minus x cubed divided by 3, all multiplied by 2/9 and evaluated from 0 to 3. And again, when I simplify, I find the same result, that x bar is 1. The location of the geometric center in the horizontal direction is at 1. For the calculus 3 formulas, the moment in the x direction is very similar to the moment in the y direction, but instead of with x, it's going to have y in the integrand. And this time, of course, we integrate with respect to y first to get y squared over 2. Again, the area of the region is 9/2, so we multiply by the reciprocal 2/9. I again squared the 3 minus x, and then I integrated and simplified, and I got again that y bar is 1. So now we can take a look at it down here on our shape. And when you're looking at it, you can tell that the black is the geometric center. That's the geometric center of this region. And the purple is instead the center of mass, which has been shifted out along that line where x equals y because it is 8 times x times y. So it's increasing with the same magnitude with respect to x as it is with respect to y. Let's take a look now at the next example, which is example 5. We want to calculate the mass, the two moments, and the center of mass of the region between the curves y equal x and y equal x squared. And this time our density function is in fact just a function of x. So rho of x and y is equal to x over the interval from 0 to 1. So the first thing we really want to do is figure out what does our region look like. So we have the equation y equal to x, and we also have the equation y equal x squared. So when we're looking at these two, y equal x, of course, is going to be the line coming through the origin of slope 1. And y equal to x squared is going to be the parabola, which is shifting up 1, right 1, left 1, up 1, right 2, up 4, etc. So it's basically this guy right here. Right, so doing my best to draw the parabola. So the region that we're talking about is the region between those two curves. So it's going to be this shaded region that we see right here. Oh, that's a really large pen, so maybe make it a little smaller. It's this region right here. So it's kind of a crescent shape with the line on top and the parabola on the bottom. So we need to find the mass, the moment with respect to x, the moment with respect to y, and then use those to compute x bar, y bar for the center of mass. So the mass, of course, is just going to be the density function in a double integral. The moment with respect to x is y times the density function in the double integral. And the moment with respect to y is x times the density function. So go ahead and pause the video while you work this one out, and then turn it back on and we'll compare our results. In order to find the center of mass, we're first going to find the mass, and then we'll find the two moments. So when I compute the mass, I take the double integral of the density function, and in this case, the density function is x. So integrating x with respect to y first just gives me xy evaluated from x squared to x, which gives me x squared minus x cubed for the new integrand. I integrate that with respect to x, and I get x cubed over 3 minus x to the 4th over 4 from 0 to 1. which gives me that the total mass is 1/12 of a kilogram. All right, now the next thing I need to do is to compute the moment in the x direction, the moment in the y direction. Moment in the x being the tendency to go off the horizontal, changing the y value. So in this case, our formula is going to be y times the density function. The density function is x, so the integrand is just xy. And when I integrate with respect to y first, I get xy squared over 2, evaluated from x squared to x. And this ends up, after simplification, to be x cubed minus x to the 5th, all divided by 2. And when I integrate this with respect to x, I get 1/2 times the quantity x to the 4th over 4 minus x to the 6th over 6 between 0 and 1. And when I simplify that, I get 1/24 kilogram meter, which is the moment. Remember, the moment is the mass times the distance. So kilogram meters is the correct units for moments. And then we compute the moment in the y direction by multiplying the density function, which is x, by the coordinate, or by the variable x, which gives us x squared for the integrand. And when I integrate with respect to y, I get x squared y, and evaluated between x squared and x, which gives me x cubed minus x to the 4th for the new integrand. Integrating that, I get x to the 4th over 4 minus x to the 5th over 5, which gives me 1/20. So then I can put all the pieces together, and in order to find the x coordinate, I take the moment in the y direction, which changes those x values, and I divide by the total mass, which I can't remember. I think we got 1/12. Yes. So I take the 1/20th and divide by 1/12. And then to find the y coordinate, I take the moment in the x direction and divide by the total mass, which was 1/12 of a kilogram. And when I work it out, I get 3/5, 1/2. So this is the center of mass, given that the density is not constant. Given that the density is not constant, that it's increasing linearly with x, we would expect the center of mass to be shifted from the centroid towards increasing x. And in fact, it is. You can see it's right here. So you know the next thing I'm going to ask you is to find the centroid. So to find the centroid, we pretend that the density is a constant so that it cancels out of our formulas. So for example, if we're looking at our equations, we can cancel the density out here and take the double integral of x dA divided by the area of that region. And then for the moment, or the y bar, we can take y dA in the double integral divided by the area of that region. So go ahead and pause the video if you want to, work out what the centroid is, and then turn the video back on, and we'll see how the centroid compares to the center of mass. Okay, let's take a look at the centroid. So the centroid, we again call it x bar, y bar. We're just pretending the density is constant. If the density is a constant, doesn't depend on x or y, then it doesn't affect the center of mass, which becomes the centroid. And so in this case, when I compute the double integral, first I'm going to find the area of the region in the denominator, and then in the numerator, for x bar, I'm finding what was the moment in the y direction. So I have x dy dx. And when I integrate each one of these appropriately, and you can see the work right here, for the area, I integrate the integrand of 1, and I get y evaluated from x squared to x. And that's going to give me a new integrand of x minus x squared. And then I integrate with respect to x, and I get x squared over 2 minus x cubed over 3, which when I reduce it is going to give me 1/6. So the area of that region is 1/6 of a square unit. Now in the numerator, I had x dy dx. So I integrate with respect to y to get xy evaluated from x squared to x, which gives me a new integrand of x squared minus x cubed. And when I integrate that, I get x cubed over 3 minus x to the 4th over 4 from 0 to 1, which is going to give me, I believe, 1/12. So I have 1/12 divided by 1/6, which tells me that X bar is at 1/2, right? So this time I found that the location of the centroid, the geometric center, the X coordinate is 1/2. And I've also got that the area is 1/6. Now this area is going to show up again in the formula with constant density in order to find Y bar. So it becomes our denominator here, and the numerator is the double integral of Y times the differential dA. When I compute Y bar, then I know the denominator is 1/6 since I've already found it in the first part. So I can multiply by the reciprocal 6/1. Integrating Y gives me Y squared over 2. Evaluate from X squared to X, which is going to give me a new integrand of X squared minus X to the 4th, all divided by 2. I pulled the 1/2 out to multiply by 6 to give me a constant of 3. And then I integrated to get X cubed over 3 minus X to the 5th over 5. And when I simplified, I got 2/5. So I basically have 1/2 comma 2/5 for the location of the geometric center of that crescent shape between the parabola and the line. Let's take a look at what it looks like on the graph. So on the graph, the geometric center is right here in purple, and you can see that it is, well, it's in the geometric center of that shape. But the center of mass has been shifted to the right towards increasing X because the density function was X. And so as X increases, it becomes more dense. It has more atoms and molecules on the right side than it has on the left side. The next thing we want to talk about is we want to go ahead and talk about three-dimensional centers of mass and what are called moments of inertia. So we're going to start with a 3D center of mass, and we're going to suppose that we have some kind of three-dimensional solid. It could be any kind of solid, but it's going to be solid all the way through. And we're going to represent it with E. So it's not a flat two-dimensional surface. It truly is 3D, length, width, depth. And we're going to let rho be the density function, but this time rho could depend on X, Y, and or Z. So any of the three main variables. This will give us the density at any particular point inside the three-dimensional solid. The total mass then is the triple integral over that solid of the density function times the differential dV. So it's very much like the lamina case where we had a double integral of the density function with dA. So it's essentially the same formula, but with a triple integral and the differential dV. Then we want to go ahead and think about what the moments are going to be. So in the two-dimensional case, we had this rotation off the x-axis and rotation off the y-axis. But in 3 dimensions, you could be rotating off of the xy plane, or you could be rotating off of the xz plane, or you could be rotating off of the YZ plane. So instead of one axis, you're not rotating off one axis, you're rotating off one of the coordinate planes. So the YZ plane, of course, would be like the screen, and rotating off of it would pull you out of the screen or back out of the screen. And if you're looking at the XY plane, it would be like our floor. And then if you rotated up or down, you would be off the floor. So when we look at these, we have a moment in the XY direction. So this would be off of the XY plane. Well, if I'm on the XY plane and I rotate up, what changed was my Z value, right? So I went up or I went down. Then it's Z that changes. So you would expect in the triple integral to multiply the density function by Z, and that's exactly what you have. Now the moment in the XZ direction, so XZ would be, well, it would be like a wall coming this way. So you have the x-axis and the z-axis. And if you were to rotate off this, you'd be changing the y value. So you would expect in the triple integral that you would multiply y by the density function, and you do. And the last one, of course, is the moment with respect to the YZ plane, which means you're going to come off the screen, which means you're changing the X value. So you have X here. So basically the variable that is missing from the subscript is the one that you multiply by the density function in the integrand. And then in order to find the center of mass, you got to find the center of mass in 3 directions. So you don't just have X bar, Y bar, you have X bar, Y bar, and Z bar. And then you would expect to take the moment in each direction and divide by the total mass. Now, X bar is going to be given by the moment in the YZ direction divided by total mass. Because again, if you're in the YZ plane and you come off of it, you're changing the X value. Y bar is going to be the moment in the XZ plane. So you're on this plane. If you come off, you're changing the Y value. And then Z bar is going to be the moment in the XY plane, because if you come off of that, you're changing the Z value. And then, of course, you just list the 3 in an ordered triple, and that will give you the center of mass. Now, if we have uniform density, then the density becomes a constant. It can factor out. It will cancel. You don't even need to compute it. It's not exactly any more than the moment divided by total mass, but it still works out if we have constant density. And we'll find that the center of mass and centroid will be the same location if we have constant density. So let's turn our attention to the next example, which is example 7. We want to suppose that we have a solid region bounded by the plane x plus 2y plus 3z equals 6, and each of the coordinate planes, the xy plane, the yz plane, and the xz plane. All right, so x equals 0, y equals 0, z equals 0. And we have a density function that depends on x, y, and z of x times y squared times z. And we want to set up the integrals to find the center of mass. Now, on this particular one, I don't really want you to go and compute them by hand. You can, you would be there a long time. So instead, what you can do if you want is you can use some kind of online computer algebra system to just give you the value of the triple integral. Or you can wait and see what I come up with. So the first thing that we're going to do is we're going to compute the moment in the xy direction, which is going to be z times rho of xyz. So z times xy squared z, so xy squared z squared. And then we need to find the limits of integration. Now that's going to be the most difficult part. The integrands are pretty straightforward. Computing the actual coordinates of the center of mass are straightforward once we have the moments and the mass. But what's not straightforward is the limits of integration of this region. So first things first, we plot everything that we have. So we have this slanted plane, x plus 2y plus 3z equals 6. We have x equals 0, y equals 0, z equals 0. So we have those 3, which I've graphed here on the left. So the yellow is the xy plane, z equals 0. And the hot pink color right here is the xz plane, where y equals 0. And the turquoise blue is the yz plane, where x equals 0. And then the brown is the slanted plane that we were given the equation for, x plus 2y plus 3z equals 6. So I need the region that's trapped inside all of these. So I can see that the plane is coming down like this, and it's going to come through the xy plane. And when it does that, it's going to create a shape here in octant 1, right? So the top of it is going to be this slanted plane, and the floor of it is going to be the xy plane. And one wall of it is going to be the pink plane, which is the xz plane, and the other one is going to be this turquoise plane, which is the yz plane. So when you do that, we know that the top is going to be the slanted plane. So we can solve this equation for z and set that as the top of our region. Then we know the bottom is going to be the XY plane, the yellow, so we can set Z equals 0 to be the bottom. Now the problem is we need to know what it looks like in the XY plane. So I need to know how this brown plane intersects the XY plane. I need to know what that looks like. So how do I find that out? Well, if I'm in the XY plane, then the value of Z is 0. So if I take my equation up here and I replace Z with 0, I get the equation X plus 2Y equals 6. So that gives me the equation of a line. That line is the intersection of the brown plane with the yellow XY plane. All right. So let's go ahead and take a look at that equation down here. So I get X plus 2Y equals 6 because I set Z to be 0. And that gives me the equation Y equal negative 1/2 X plus 3. So now I can guess that Y is going to vary from Y equals 0, right? So Y equals 0 is basically the x-axis, so right here, up to that line. But I don't know what X is going to vary between. So now I've got 2/3 of the limits of integration. I know that the base is Z equals 0, the top is Z equal whatever that slanted plane was. Y is going to go from Y equals 0 up to Y equal negative 1/2 X plus 3, but what about X? Well, in order to figure that out, you need to find where it crosses the x-axis again. So I can take this equation right here and figure out what region is trapped there in quadrant 1. It turns out to be 0 to 6, but let's take a look at this over here on CalcPlot 3D. So here's my region. It's a little small. Let's blow it up. Oh, no, that didn't work too well. Okay, there we go. I'll just blow it up this way. All right, so I'm trying to figure out what it looks like. So I've got the brown plane for the top, the XY plane for the bottom, the turquoise YZ plane for this side, and the pink XZ plane for this side. But I need to know what it looks like in the XY plane. So one thing you can do is hold the Alt key and press Z, and you're going to find that you have this equation given here, which I think was, what did it turn out to be? Negative 1/2 X plus 3. So we have negative 1/2 X plus 3. And when Y is 0, we get that X is 6. So X is going to vary from 0 to 6. So this gives you all 3 of your limits of integration for the triple integral. So let's go back now to our shape. So here's our shape again. Well, let me do the home key. That will give us a better region. So I'm trying to figure out, when I'm looking at this, what the center of mass of this is. The density varies, right? X, Y squared, Z. So in the Y direction, it becomes denser faster than it does in the X or the Z direction. The X or Z, they're both linear, but in the Y direction, it's Y squared. So it's increasing at a faster rate in that direction. So I would expect the center of mass to maybe be pulled in the direction of increasing Y more so than increasing X or Z, although as X and Z increase, it will increase. All right, so let's go ahead now and set up our integrals for this particular one. So our mass is going to be the integral X is varying from 0 to 6. Y is varying from 0 to negative 1/2 X plus 3. And Z is varying from 0 to 2 minus X over 3 minus 2Y over 3. Now, how did I get that? When you think about that one, you want to come back to your equation for the plane And you just want to solve it for z. So move the x plus 2y to the right by subtracting, and then divide everything by 3. And you'll get the upper limit of integration. Right? So once we have that, then to find the total mass, we multiply by the density function and our differential. So x, y squared, z, dz, dy, dx, right? So that will set up the mass. Now we have 3 moments. We have the moment in the xy, the moment in the xz, and the moment in the yz. Each one is the density function, xy squared z, multiplied by the missing variable. And the limits of integration are going to be identical for all of them. So go ahead and pause the video while you write these down, and then turn the video back on, and I'll share with you the actual results of this. So when I computed the mass, I ended up with 54 divided by 35. When I computed the moment off the XY plane, which is going to affect the Z value, I multiplied the density function by Z, which gave me an integrand of XY squared Z squared. And that gave me 27/35. Now that's kilogram meters, all right? Or kilogram meters squared, since we're moving off 2 planes. And then the moment off of the YZ plane, which is like the screen, is going to change the X value. So you multiply the density function by X to get an integrand of X squared Y squared Z, which gives us 81/35. And finally, the next thing I do is compute the moment off of the XZ plane, which is measured this way, coming straight out of the screen towards you. And when you rotate off of that, you're going to change the Y value. And so we multiply the density function by Y, giving us an integrand of XY cubed Z. And when we integrate with the same limits of integration, we get 243 divided by 140. Now, when we're looking at this, we've got our mass up here at the top. So all of our moments are going to be divided by the mass, 54 divided by 35. In order to find a particular coordinate, you look for the one where that variable is missing. So the moment off the XY plane is going to affect Z. So to get Z bar, we would take our 27/35 and divide by 54/35. And when we're trying to find, in this case, X bar, this is the tendency to rotate off the YZ plane. Then we take 81/35 and divide by 54/35. And finally, when we're looking for Y bar, we'll take our 243 divided by 140 and divide by our 54/35. And when you work all 3 of these out, you get that the center of mass for that triangular solid is 3/2, 9/8, 1/2. So in this case, when we look at it out here on CalcPlot 3D, if I can blow it up a little bit, I've made it yellow, but I didn't want to make it too large because then it kind of shifts it a little bit. So you can see where it is right there, right? So it's definitely moving with respect to the different axes, all right? But in fact, it's probably moving more rapidly with respect to the Y because it's Y squared inside of the density function, right? So it's been shifted sort of out and up, but out more along the Y than along the X and the Z. Now let's take a look at what's called moment of inertia. Now this is different from the moment we've been talking about, although it's related, which is why they both have the name moment. Inertia is the tendency to maintain whatever your current mode is. So if you're at rest, it's the tendency to stay at rest. If you're moving, it's the tendency to keep moving. In other words, not to change what you're doing. The moment of inertia in this case refers to the resistance to being moved. So the moment of inertia, we're talking about a torquing pattern, but it's not actually torque. Torque is a movement force. So you're rotating through some kind of radial arm. Whereas moment of inertia is measured the same way, but in this case, it's the force multiplied by the distance. But again, it's a resistance to being moved. All right, so it's a static force. It's not actually moving. It's not a movement force. It's a static force. So when we're looking at the moment of inertia, and we think about it as this resistance to being rotated, it's related to both the mass of the object, and you might expect the more massive it is, the more it resists rotation, and also the distance of the object from the rotation. Was it Archimedes who said, give me a lever long enough and I will move the earth? Because if it's far enough away, it's easier to move. So if you're closer, it's harder to shift, right? But if you're further away, you have a longer lever, then it's easier to move. So it's related to both the mass and the distance from the object to the point of rotation. So we often split moment of inertia up into horizontal and vertical components. And sometimes we talk about it about the origin as well, which would lend itself more towards polar coordinates. So let's say that we have some fixed point in space and we want to measure the resistance to rotating about that fixed point. Well, it turns out that that is equal to the mass times the radius distance squared. So the distance from the point of rotation, which is here, out to the mass is r, and then whatever the mass of the object is multiplied by that distance squared is the moment of inertia in one dimension. Now we want to think about what it's like if we have two dimensions. So we're going to split it up into horizontal and vertical. And then we're also going to consider what it would be like if we rotated it about the origin, which would be sort of using like polar coordinates. So in the case of the moment of inertia with respect to x, you should not be surprised to see y in the formula. So it turns out, and we're not going to go through the derivation of these formulas, but it turns out to be the double integral of y squared times rho of xy with respect to the area differential. So if you think about it, this y squared, this is the distance from the horizontal axis. And we said that the moment of inertia is the mass multiplied by the distance squared. So it makes sense that when you're looking for the inertia, the moment of inertia with respect to x, it's going to be y squared basically times the mass, because the mass is given by the density function integrated over dA. Then when you want the moment of inertia with respect to y, then again, you're talking about resistance to rotating off of y. You would expect then that the distance is from the y-axis to the point mass, which would be x squared times the density function integrated with respect to dA. All right. Now, what if we were, instead of rotating off of a vertical and off of a horizontal, if we're talking about rotating around the origin in a circular motion, basically? Well, then our distance is going to be the radius of that circle, which we know is x squared plus y squared, right, from the Pythagorean theorem. And then we multiply by the mass, which is the density integrated over dA. So this gives us three different formulas, one for the horizontal moment of inertia, the vertical moment of inertia, and what's called the moment of inertia around the pole, meaning the polar axis. And the pole, of course, is going to be the origin. So the polar moment of inertia, and we write that I sub 0, right? So let's look at example 6, which is our last example. We have a flat lamina, and it consists of the part of the circle of radius 2, which is centered at the origin and lies only in quadrant 1. So it's a quarter circle. And the density at every point is given by 4 times x squared plus y squared. Now we want to find two things. We want to find the center of mass, which we know we need to find the mass, and we need to find the moment in the x direction and the moment in the y direction. That doesn't have anything to do with moment of inertia. Then after we've computed x bar, y bar for the center of mass, then we want to find the moment of inertia about the pole, or the polar moment of inertia. So this is about the origin. And for that one, remember that our distance is the radius of that circle, which is x squared plus y squared, or r squared. And it does lend itself to polar coordinate systems. So you may want to consider converting. So go ahead and pause the video and at least work out the center of mass. So find the mass, find the moment in the x direction, moment in the y direction, and then compute x bar, y bar, and turn the video back on, and we'll look at the moment of inertia about the pole together. The first thing to recognize on this problem is that it's best done with polar coordinates. Because we have a quarter of a circle and we're looking for the moment of inertia about the origin, or the polar moment of inertia, it makes sense to use the polar coordinate system. That means I need to convert my density function 4 times the quantity x squared plus y squared into 4r squared. This also means that I need to think about this quarter circle in terms of r and theta. R goes from 0 to 2, and theta goes from 0 to pi divided by 2. To find the mass, I integrate the density function over that region. So 4r squared is the density function, but the polar coordinate differential is r dr d theta. So that gets me 4r cubed. So when I integrate, I get 4r to the 4th divided by 4, just r to the 4th, evaluated from r equals 0 to r equals 2, which just gives me 16 as my new integrand for the theta integral. And then when I integrate, I get 16 theta from 0 to pi over 2 gives me 16 times pi over 2, or 8 pi kilograms. Now, in order to find the center of mass, I need to find the moment in the x direction and the moment in the y direction. So to find the moment in the x direction, I multiply the density function by y. And to find the moment in the y direction, I multiply the density function by x. However, because we're using the polar coordinate system, we need to convert our x and our y into their polar representation. So when I'm computing the moment with respect to x, I have y times the density function 4r squared times the polar differential r dr d theta. But y can be written as r sine theta. So I have r sine theta times 4r squared times r, which gets me 4r to the 4th sine theta, dr d theta. Then I integrate first with respect to r to get 4/5 r to the 5th sine theta, evaluate from 0 to 2 for r, and that gives me 128/5 sine theta, d theta, between 0 and, looks like I wrote 2 pi up here. I'm not sure where the 2 pi came from. That should be pi over 2. I think I was just writing and not thinking. So the next step is going to be to integrate with respect to theta. So the integral of sine is negative cosine. And then when we evaluate from 0 to pi over 2, cosine of pi over 2 is 0. Cosine of 0 is 1. So I get 0 minus 1, or negative 1. But multiplied by the negative gives me a positive 128/5. So to find the y coordinate, I'm going to take that 128/5, and I'm going to divide by the 8 pi that I got for the mass. Right? Now, to find the x coordinate, I need to find the moment in the y direction, the tendency to rotate off that y. So I'm going to take x times the density function for r squared in polar coordinates, the polar differential r dr d theta, represent x as r cosine of theta, to get 4r to the 4th cosine theta dr d theta. Then that becomes 4/5 r to the 5th cosine of theta from 0 to 2. So again, I get 128/5, but this time multiplied by cosine theta. Cosine's integral gives me sine, And when I evaluate sine of pi over 2 as 1, sine of 0 is 0. So I just get 1. So again, I get the same thing, 128 over 5. But that's because of the symmetry of the location that we have. The quarter circle is symmetric with respect to the circle. And for r squared, it's increasing with respect to the radius, which is how it is symmetric. So that's why they came out to be the same. That's not typically the case. And then I can compute the center of mass by dividing my two individual moments by the total mass, 8 pi. And I get 16 divided by 5 pi for each one of those. Now, the next thing we were asked to find is the polar moment of inertia. So that's the resistance, like it doesn't want to move, to rotating around the origin. So with the origin being the fixed point. So the distance out to the mass is the radius, which is x squared plus y squared, or in our case, in the polar coordinate system, r squared. So to find the polar moment of inertia, we're going to take the density function multiplied by that arm, that radial arm of r squared, and then with the polar coordinate system differential r dr d theta. So this gives us 4r to the 5th dr d theta for the inside. And when we integrate, we get 4r to the 6th over 6. 4/6 reduces to 2/3. We evaluate from 0 to 2. 2 to the 6th is 64, which gives me 128/3 for the new integral with respect to theta. And that gives me 128/3 theta from 0 to pi over 2, gives me pi over 2 times 128/3, which gives me 64 pi thirds, and this would be in terms of kilogram meter squared. So this is the resistance. It's a static force. It's not moving. It's still to being rotated about that arm. Okay. Now we have just a little bit left to talk about. Let's see. I did go ahead and graph for you where the center of mass on that circle was. So you can see it's right here. And again, the density function came out to be 4r squared. So as the radius increases, it's pushing out along the radius. And of course, it is symmetric with respect to the radius because it's a quarter of a circle. So it's moving directly outward. All right. Let's go ahead now. Now, of course, that wouldn't be the geometric center, which would probably be somewhere like right around here. Okay. And we could find that by integrating again, but considering the density to be constant, not 4r squared. We could just let it be 1. Now, what if we wanted to talk about three-dimensional moments of inertia? So that would be x, y, and z. So this would be the resistance to being rotated off the x-axis or the y-axis or the z-axis, depending on which way you want to turn them. In order to do that, the moment of inertia, this resistance to being rotated, is going to give you a triple integral if you've got a solid, since it's a three-dimensional object. And the moment of inertia about x, this tendency to wobble off the x-axis, is going to have y squared plus z squared, which would be the distance out to the x-axis along this rotation in the polar coordinate system, but translated to that plane, multiplied by the density function. To find the moment of inertia with respect to y, then we would have the radial arm, but in this case, x squared plus z squared, so translated into the xz plane. And then, of course, the tendency to rotate off the xz plane changes the y value, multiplied by the density function. And then for the moment of inertia with respect to z, the tendency to want to rotate off z, you have to be in the xy plane. So this is the radial distance, x squared plus y squared in the radial plane. This is really r squared. And then we have multiplied by the density function with the differential dv to get the mass. So again, in all cases, we're getting mass times the radial distance squared, right? We have one last idea to cover, which is related to what we've been talking about recently. And this is what's called the radius of gyration. So this is a very weird thing. It's just sort of a fun little topic to talk about. You probably don't have any homework problems on it. But every once in a while, we need to know what it would be like if we could concentrate the mass at a point around where we're rotating. So at a fixed distance from some point of rotation, all right? So R. So we have a point mass, all right? And we need to know how far that radius would be to have the same moment of inertia as our object. So this radius is known as the radius of gyration, and it can be found using the moment of inertia with respect to X, moment of inertia with respect to Y, and the total mass. And you can also, of course, compute the radial version of this, the resistance to going around a polar axis. The last one actually turns out to probably be one of the most useful. This one is the radius that you would need if you could concentrate the mass at a fixed distance away from the center. So it's going to tell us how far the entire mass of the object could be concentrated. So let's take a look at a picture here. So let's suppose our real object is this solid disk of radius uppercase letter R, and the total mass of this solid disk is M. What I want to know with this radius of gyration is if I could take all the mass that's evenly distributed throughout this disk, and I could concentrate it in a ring around the rotation point, what would the radius of that mass ring be? So all the mass is now in this thin band around this rotation point. And whatever that radius is, that's the radius of gyration. So hopefully you've enjoyed learning a little bit more about this, and you'll be ready for the next section. So we have one section left to discuss for chapter 5, and that's what's called change of variables. And when I first heard of change of variables, I thought changing the order of integration, but that is not at all what it means. It is an actual change of variables. We've done this before when we were in Calculus 1 and we did U substitution. So we changed from integrating with respect to X to integrating with respect to U. We completely changed the variable. And we also did this in trig substitution in Calculus 2, where we changed from integrating with respect to X to integrating with respect to theta. So we have some experience at this, but I will warn you, it is a quite challenging section. So you're going to want to allow extra time in order to learn the material in the last section, which is in the next video coming up soon.